Why did Mars become a dead planet? Dear traveler, greetings. Today we set out to explore the remnants of a lost world, a red planet, barren and frozen, swept by dust winds. But it wasn't always like this, because once upon a time, Mars was different. Rivers flowed there, lakes glistened under a thick sky, and perhaps even life breathed there. But something broke the balance, a silent cataclysm, a slow planetary agony. The water evaporated, the atmosphere extinguished, and Mars entered an eternal winter. What really happened? Why did this planet, so close to Earth, sink into oblivion? And what if the traces of another story, a vanished life, were still there, buried under the red dust? But before embarking on a new adventure, don't forget to like the video and subscribe to the channel to not miss anything. Thank you, and have a nice trip. At the beginning of our cosmic story, long before the appearance of Earth or Mars, a vast cloud of gas and dust drifted in interstellar space. About 4.7 billion years ago, 2.9 billion miles, this cloud, on the verge of collapsing under its own gravity, transformed. It was an immense veil made of hydrogen, helium, and countless solid particles enriched with chemical elements. Disturbances or waves from stellar explosions then triggered the collapse of its densest regions. Inside, the matter concentrated and heated up. This process would give birth to a new star, the proto-sun. At the heart of this initial cloud, a particular component draws attention, aluminum-26. Probably originating from a nearby supernova, this unstable isotope releases heat as it decays. This energy adds to that of gravitational collapse and raises the temperature of the forming disk. By decaying, aluminum affects how the components of the solar system condense or evaporate, imprinting its mark on the chemistry of the disk. At the center, as the proto-sun organizes itself, the rotation of the cloud leads to the formation of an accretion disk. This disk gathers gas and dust rich in metals and minerals. Near the core, the temperature rises, causing volatile compounds to evaporate. Further away, it drops. Around 3 astronomical units, 279 million miles, water transitions from vapor to ice. This thermal boundary, known as the frost line, separates two worlds, that of dry materials and that of ices. Beyond this boundary, water freezes into icy grains that mix with solid dust to form pebbles. Closer to the center, the intense heat prevents ice from surviving. The materials there are dry, composed of silicates and metals. This difference will influence the distribution of water in the future planets. Water will concentrate in the outer region, while the warmer inner area will gather little. During this phase, the water of the disk retains an isotopic imprint. The ratio between deuterium and hydrogen, set very early, allows tracking the origin of the grains. Deuterium, heavier than hydrogen, incorporates into water molecules. By analyzing the proportion of these isotopes in meteorites and other samples, researchers can determine the position and timing of their formation. This distribution influences the composition of celestial bodies and the future presence of water on planets like Earth. Simultaneously, the disk sees the emergence of calcium and aluminum-rich inclusions. These solid structures form early under extreme conditions. Their dating goes back more than 4.56 billion years, 2.83 billion miles ago. Shortly after, small silicate spheres called chondrules emerge. Their formation, separated by less than 50,000 years from the inclusions, reveals an intense and rapid dynamic. Today, these two types of primitive grains serve as benchmarks for dating the beginnings of the solar system. The disk also contains hydrated minerals. These phases contain water integrated into their crystalline structure. Phalosilicates, for instance, retain water in their composition. Once incorporated into celestial bodies, these minerals carry their water as a solid reserve. This water integrated into the rock helps to understand how the water condensed beyond the frost line could migrate and reach areas closer to the sun. Another phenomenon comes into play: streaming instabilities. In the disk, gas and solid particles do not rotate at the same speed. This difference generates turbulence where material can clump together. These instabilities concentrate grains in certain areas. Large, ice-rich grains can cluster together, while smaller, often dry grains remain elsewhere. This prevents a uniform distribution of materials and creates complex currents within the disk. For Mars, these instabilities influence the water inventory. Formed midway between the hot center and the cold regions, its composition will depend on the materials that reach its orbit. At this point, Mars does not yet exist, but the components of its formation, dust, pebbles, and hydrated minerals, are already circulating in the disk. These processes will determine which elements reach its area and which remain distant. During these decisive millions of years, a dance of matter takes place around the proto-sun. The forming star emits winds that disperse some of the gas. Aluminum continues to release heat. The regions close to the center reach extreme temperatures where only metals and silicates survive. Meanwhile, farther away, water condenses and enriches the material. This scene, marked by turbulent movements, sees matter concentrating in certain areas favorable to the birth of planets. This fragile chemical balance determines the composition of the worlds to come. Water, crucial for life, is not evenly distributed. From the outset, a thermal contrast is established. Inside the frost line, water evaporates, while beyond it, water solidifies. This contrast is reinforced by streaming instabilities, which allow some places to become enriched in ice and others to remain dry. In the early times, the dust is extremely fine. These tiny grains gradually aggregate into larger structures. In cold regions, ice promotes this aggregation. Elsewhere, heat complicates this process. In these hot zones, the formation of planetesimals follows a different chronology and chemistry, depending on the availability of water, temperature, and the nature of the minerals present. The solar nebula thus becomes a true laboratory of chemical reactions. The study of ancient meteorites still reveals these traces today. Phalosilicates bear witness to the existence of water from this era, integrated into their structure. Their dating shows they form at the same time as the first inclusions, revealing the rapid pace of these initial transformations. The stage is set. The proto-sun lights up, heating the surrounding disk. Near the center, ice disappears, leaving only dry grains. Further out, ice is preserved, enriching the dust with volatile elements. This thermal gradient, combined with turbulence and instabilities, sorts the materials. Aluminum-26, through its heat, accelerates certain processes, locally altering the disk's chemistry. At every moment, the nebula is traversed by movements. The interactions between particles, the exchanges between gas and dust, all occur very quickly. The proto-sun has not yet triggered fusion in its core, but its radiation is already shaping the environment. Its winds gradually disperse the light gases, leaving only solid particles in the plane of the disk. The future planets emerge under very different conditions, depending on their position. In this turmoil, the ratio between deuterium and hydrogen stabilizes. This isotopic signature becomes a true identity card of water. The proportion of deuterium varies according to temperature and region. Chemical reactions and radiation effects modify this content. Current measurements derived from meteorites or space missions thus trace the path of water in the protoplanetary disk. At the end of this phase of a few million years, the disk is already structured. The center is hot, poor in water, rich in silicates. The outer zones teem with ice and hydrated minerals. Around the frost line, a mix of volatile and dry grains accumulates in traps where material assembles into larger blocks. These planet embryos are already marked by their water richness and specific composition. Between 4.7 and 4.56 billion years ago, the foundations of the solar system were established. The cloud collapsed, aluminum heated up, water condensed, isotopes became fixed, and instabilities channeled matter. These phenomena set the initial conditions that would define the future distribution of water. Phyllosilicates, in particular, prove that water actively participated in the chemistry of the disk from the very beginning. In this dusty environment, illuminated by a still unstable proto-sun, the ingredients of life began to form. Meteorites, remnants of that era, preserve these traces. These fragments, sometimes modest in appearance, reveal the thermal and chemical conditions of the disk. By observing their structure, we discover dry grains and others enriched with ice, reflecting the intense activity around the young sun. Understanding the genesis of the solar system means realizing that the sun was not born in calm, but at the heart of a whirlwind where each area of the disk had its own climate. The cloud's collapse set off a series of pivotal events. Water's journey from vapor to distant ice originates in this tumultuous phase. The birth of the proto-sun is also the birth of a world in the making, where each planet would receive a unique inheritance of water and matter, shaping the diversity we observe today. When we think of Mars, we picture a frozen desert, crisscrossed by eroded valleys. Yet its origins trace back to a tumultuous period over 4.5 billion years ago. It was during a rapid phase that the planet assembled from the swirling debris of the solar nebula. This key moment, completed around 4,054 million years ago, shaped the planet's interior, preparing for the arrival of water and the first climatic upheavals. This narrative explores the atomic clocks, revealing the birth of its core, the movement of Jupiter that redistributed matter, and a colossal degassing that enveloped the young planet in a thick atmosphere with brutal downpours. It is a journey into an intense past where every cosmic dust built the red planet. To understand this period, one must grasp the principle of geochemical clocks. These markers allow us to date the formation of the Martian core. Two isotopes play a central role, hafnium and tungsten. The former, unstable, disintegrates and gives birth to the latter. Hafnium binds more to the rocky layers, while tungsten migrates to the metals of the core. By analyzing the proportions of these elements in Martian meteorites, researchers trace back to the moment when the planet differentiated its metallic core from its rocky envelope. It's a mechanism of fearsome precision, comparable to a clock powered by the laws of physics. The results reveal that this differentiation finished in less than 4 million years after the formation of the very first solids of the solar system. These inclusions, rich in calcium and aluminum, are the oldest known temporal markers. 4 million years may seem vast, but on a cosmic scale, it's a flash. In comparison, Earth took 5 times longer to reach the same stage. This is why Mars is nicknamed the lightning accretion, a planet eager to define itself with an already distinct geological identity. With this backdrop set, we must now mention a major event, the Grand Tack. This hypothesis describes a scenario of planetary migration during which Jupiter, after slipping towards the inner solar system, changed direction to move back outward. This staggering trajectory disrupted the course of thousands of material blocks, the planetesimals. These fragments, composed of rock and ice, are the building blocks of planets. As it passed through the region where Mars was gestating, Jupiter disrupted the distribution of materials. The impact of this movement is clear. It limited Mars's growth. Simulations backed by isotopic data show that this planet achieved only just over 10% of Earth's mass. Without this movement of Jupiter, Mars would likely have been more massive. This small size had consequences: weaker gravity, a less dense atmosphere, and a distinct evolution. This same mechanism likely delivered a large quantity of ice to Mars, from planetesimals coming from colder regions, beyond the line where water turns to ice. By examining this water supply, scientists estimate that Mars received between 1.5 to 6 times the volume of water contained in Earth's oceans. This figure gives an idea of the potential abundance. If this water could have been preserved on the surface or underground, it would have represented a considerable reservoir. But its state and distribution depended on a great number of factors, including the temperature, pressure, and internal dynamics of the young planet. The richness in ice of planetesimals, coming from the outer regions of the solar system, is explained by the low temperatures of these areas. There, water condenses easily, also trapping other gases like carbon dioxide. These frozen bodies, moved to the Martian orbit, gradually enrich the chemical composition of the planet. Imagine blocks several kilometers or miles in size, crashing or integrating into the Martian surface, bringing with them precious reserves of water. Then comes a spectacular moment, cataclysmic degassing. A still hot planet then releases its internal gases. Water vapor and carbon dioxide escape from the mantle, forming a primitive atmosphere. Estimates indicate pressures exceeding 100 times that of current Earth. A dense and suffocating atmosphere envelops the planet, trapping heat and amplifying the greenhouse effect. This phenomenon triggers rains of extreme intensity. As the vapor condenses in the high layers, immense drops fall on a still young surface. The sky is darkened by dust. Storms break out over a cooling ground. The weaker gravity does not lessen the power of these precipitations. Ephemeral rivers form, and lakes fill the basins. All of this could have happened in less than 10,000 years after the crust solidified. The speed of this transformation is striking. Barely had the crust solidified when water already covered it in places. Water accumulated during accretion had infiltrated the cracks, condensed in the atmosphere, and fell back as rain. Degassing further enriched this gas envelope, reinforcing the greenhouse effect and keeping the water in a liquid state on the surface. This moment of transient lakes and seas fascinates, as it opens a window into a past where water was omnipresent, even briefly. Researchers track the signs of this wet past in the oldest Martian rocks. Some outcrops retain the chemical trace of contact with water. Minerals form in these conditions, indicating an exchange between rock and an ancient liquid. Even if erosion or later impacts have erased many of the proofs, robots and probes continue to search for these clues. The most astonishing thing is this duration. Barely 10,000 years between a frozen surface and massive precipitation. The heat generated by impacts, radioactivity, and internal friction remains intense. The metallic core sets in place, gases accumulate, then suddenly escape. The atmosphere becomes laden with vapor and carbon dioxide. Rain falls, rivers form, and the planet is shaped in the blink of an eye. This degassing, far from being destructive, creates the conditions for an atmosphere. It also brings the necessary ingredients for complex chemistry. On Earth, water, minerals, and energy contributed to the emergence of life. It is possible that a temporarily favorable climate existed on Mars, even briefly, even without consequence. Comparing this period to Earth's history is thought-provoking. If our planet had followed such a rapid pace, continents and oceans might have appeared sooner. Mars shows us that each world follows its own path, shaped by unique events, chances, and external forces. Its express formation triggered a cascade of phenomena that left their mark even before the planet stabilized. At the start of this phase, about 4.53 billion years ago, Mars has just been born in a turbulent universe. Its appearance bears no resemblance to the frozen desert we know. Imagine, above this molten sphere, the extreme heat emanating from a world under construction. This energy, resulting from collisions and the disintegration of radioactive elements, creates a vast ocean of molten rock. The entire surface is engulfed under thick, burning lava. The temperature far exceeds thousands of degrees, maintaining minerals in a liquid or semi-liquid state. The spectacle would be of a boiling sea, traversed by bursting bubbles in a primitive atmosphere. In this incandescent bath, the components constantly mix. The heaviest minerals sink to the depths, while the lighter ones accumulate on the surface. This sorting occurs through progressive crystallization. Crystals containing iron or magnesium appear first and sink, while those rich in silicon or aluminum form later and float. In a few tens of thousands of years, this process structures the planet into distinct layers. This rapid sorting gives birth to a crust that researchers call prototharchan. It reaches 50 kilometers or 31 miles in thickness and constitutes the first solid envelope. This term evokes the origin of large volcanic regions like Tharsis. This thin but already differentiated crust results from the progressive cooling of the magma and the mixing of heavy and light minerals. On a planet smaller than Earth, such a thickness is entirely plausible. During the first 20,000 years, the ocean of molten silicate remains animated by powerful internal currents. The heat causes the hot material to rise and the cooling material to sink. This incessant mixing maintains the fusion, fueled by the heat released from radioactive elements. As the surface solidifies, a thin crust forms, fragile and unstable. It can break, sink, or sometimes form a more stable foundation. Gradually, the liquid transforms. Iron and magnesium silicates accumulate in the deeper layers, while those rich in aluminum, calcium, or sodium gather elsewhere. The mantle then begins to form under this nascent crust. During this phase, certain minerals also capture water molecules within their structure. Even in this burning context, a degree of moisture is already present, inherited from the planet's formation or released from within. It is in this chaotic framework that minerals capable of recording the environment appear. Among them, zircon. This crystal withstands heat and traps uranium, which slowly turns into lead. By analyzing their composition, researchers can date their formation. Zircon can also enclose fluid traces, capturing clues about the water present in the magma or in rock fissures. Billions of years later, a fragment of Mars is found on Earth, the meteorite NWA 7034. It contains zircons dated to 4.48 billion years. These crystals reveal the existence of a solid and differentiated crust already in place. They also testify to the cooling of the magma ocean and the internal organization of the young planet. More surprisingly, these zircons contain traces of water. Despite the burning environment, it is likely that vapor infiltrated the fissures. This water could have come from internal degassing or hydrated material accumulated during formation. It existed as very hot vapor or fluid between the liquid and gaseous states. The zircons have kept the memory of these discrete contacts between water and rock. This does not mean that oceans covered Mars at that time, but that pockets of vapor or fluids formed locally. This internal water would have weakened the crust and initiated underground circulations. In these circuits, water interacts with minerals, altering their structure and shaping the primitive geology. The formation of a thick crust is a crucial step. Once in place, it becomes the base of all subsequent processes. Mars continues to cool, and the gases released accumulate in the atmosphere. Some condense in the coldest regions. In this still warm world, vapor dominates, but cooler areas trap these fluids. There, new hydrated minerals begin to form. The heat produced by uranium, thorium, or potassium is maintained for millions of years. This energy extends magmatic activity, allowing the crust to renew. Gradually, the cooling prevails, and the magma retreats deeper. The crust slowly thickens. The zircons discovered in NWA 7034 are an invaluable archive. In the laboratory, their composition is precisely analyzed. The ratios between uranium and lead reveal their age. These measurements have shown that some crystals date back to the very first Martian phase. They confirm that differentiation and the presence of water existed from the planet's beginnings. The presence of a thick crust also reveals the speed at which Mars lost its magma ocean. In just tens of thousands of years, the surface transitions from a liquid to a solid state. This crust forms a thermal barrier. Deep fractures allow heat and fluids to escape. These faults will play a crucial role in the formation of volcanoes and underground circulations. At that moment, the planet's interior remains active. Convection continues, fueled by internal heat. The crust undergoes stress, causing uplift or slippage. Certain areas are more exposed to water vapor. The discovered zircons seem to have formed in rocks, crossed by fine veins containing these fluids. Vapor, in contact with magma, leaves its chemical imprint in the crystals. Crystallization and differentiation prepare the planet to host more complex geological processes. The separation into layers conditions the circulation of heat and the distribution of elements. Some remain in the mantle, others concentrate in the crust. This imbalance determines future eruptions and the composition of released gases, including water vapor and carbon dioxide. The zircons, 4.48 billion years old, reveal a world more humid than previously imagined. Even in small quantities, water played a role from the start. It circulated in rock, modified minerals, and became trapped in the crust. These indications demonstrate that Mars already had hydrothermal activity potential long before becoming the arid planet we observe today. Between 4.53 and 4.48 billion years, Mars undergoes a decisive phase. The magma ocean gives way to a stable crust. This shift, lasting a mere 20,000 years, lays the foundations for its internal structure. During this time, in the less hot regions, vapor infiltrates the rock, leaving its trace in the minerals. The zircons of NWA 7034 bear witness, carriers of a memory several billion years old. Even today, images of Mars give the impression of a frozen world, but the rocks tell a different story, that of a young planet in fusion, sculpted by fire and shaped by water. The crust, the magma, the vapor, all intertwined in an intense narrative. Under this ancient sky, one can discern a planet animated by unsuspected vitality. Thus, around 4.48 billion years, the magma ocean disappears. Mars now displays a differentiated structure. Its crust, mantle, and core are in place. The internal forces will continue to animate it. At the surface, the Proto-Tharsian crust will become the foundation of large geological regions. The traces of water, trapped in the crystals, remind us that a dialogue has always existed between rock and moisture. Between 4,480,000,000 and 4 billion years ago, Mars went through a crucial period. At that time, the planet housed an invisible force that played a determining role, the internal dynamo. It generated a global magnetic field, enveloping the planet like a protective mantle. Mars had just completed its formation. Its core, still hot and fluid, triggered circulations of conductive material that produced lines of force around the planet. This field, although weaker than Earth's current one, reached at least 1 microtesla on the surface, an intensity sufficient to influence its immediate environment. To understand the significance of such a field, it is important to recall the danger posed by solar winds to a planet without a shield. The sun continuously emits a stream of charged particles moving at high speed. When a planet lacks magnetic protection, these particles directly hit its atmosphere, gradually stripping away its gases. On Mars, the global magnetic field formed a barrier, the magnetosphere, which forced these particles to bypass the planet, thus reducing their capacity to carry away its air. This is where the process of hydrodynamic escape comes into play. Under the prolonged effect of the solar wind, the lightest molecules, like hydrogen, escape easily. Since hydrogen is an essential component of water, its loss also means a gradual loss of Martian water. The Martian dynamo, by limiting this escape, thus played a crucial role in preserving surface moisture. To generate this field, Mars had to maintain a hot and fluid core, composed of a mix of iron and metallic elements. Shortly after its formation, the heat produced by accretion and radioactive decay maintained a partially liquid core. This liquid, in motion, transported the heat outward. As it circulated, it generated electric currents, and these currents, in turn, generated the magnetic field. Thus, Mars's first shield was born. This field never equaled that of the Earth, but it remained sufficient to slow down atmospheric erosion, particularly the loss of hydrogen. Thanks to this magnetic envelope, Mars managed to retain some of its water and thereby sustain a more temperate climate for several 100 million years. But this protection did not last. Around 3,900,000,000 years, around 4 billion years ago, the dynamo faded, perhaps even to the point of extinction. As long as the internal heat remained sufficient, the currents persisted. But as it cooled, the core became more rigid. Convection weakened. Massive impacts might also have disrupted the circulation inside the core, weakening the magnetic mechanism even further. The system eventually declined. This decline was probably not instantaneous. Initially, the field weakened. The atmosphere, then less protected, was subjected more to the assault of solar wind. Erosion intensified, hydrogen loss accelerated, and water began to disappear more quickly. Magnetized rocks in the Martian crust show that the field was strong in ancient times, but its trace diminishes after 3,900,000,000 years. As long as the dynamo was functioning, it formed a magnetic shell around the planet. When it disappeared, solar particles reached the upper atmosphere without obstacle, carrying away hydrogen and breaking water molecules. Mars then began a slow drying process. Giant impacts occurring at the same time might have exacerbated this loss. By striking the surface, these collisions could have melted the internal layers, released gases, and caused shockwaves capable of disrupting the dynamics of the core. Simultaneously, part of the atmosphere might have been ejected into space, further worsening the water loss. Some Martian minerals show that they have retained residual magnetism. This fossil magnetism suggests that the field existed in early times, but that it disappeared afterward. Thanks to paleomagnetism, scientists reconstruct this evolution by studying the orientation of fossil fields in the rocks. The link between magnetic field and water is direct. As long as the dynamo was active, it slowed the loss of atmosphere. When it ceased, water vapor evaporated more quickly. Hydrogen, ripped away by solar winds, could no longer be retained. Water became scarce. Mars became drier, colder, and less hospitable. It is possible that some regions retained pockets of local magnetic field, but these enclaves were too limited to provide planetary protection. Without a global field, solar winds had free access to the Martian atmosphere. $3,900,000,000 years, around 4 billion years, thus marks a turning point. Before this date, Mars was better protected, with a denser atmosphere and the potential to maintain liquid water. Afterwards, without a shield, atmospheric erosion accelerated, gradually draining the planet of its moisture. The losses were immense. Simulations and analyses confirm it. Global cooling, the drop in pressure, and solar erosion transformed Mars into a dry world, incapable of retaining liquid water on its surface. But how do we know all this? Thanks to satellites, Martian meteorites, and measurements of ions escaping from the atmosphere. These elements, when combined, tell the story of Mars' dynamo. We now know that a field of at least 1 microtesla allowed Mars to retain some of its water. Then, after its extinction around 3,900,000,000 years ago, the solar wind took advantage by stripping away the remaining water vapor. The planet shifted into a new era, one of a dry and inhospitable climate. Now imagine you are gliding above the young Mars. The magnetic field still beats, deflecting solar gusts. Shallow lakes gleam under a denser sky. Then, slowly, this field fades. The atmosphere lightens, the planet cools, the water evaporates. Only some fossil traces remain in the ancient rocks. Scientists continue their calculations. They still measure leaks, question rocks, and study residual magnetism. They wonder if this ancient shield could have favored the emergence of life. For as long as Mars had a thick atmosphere, surface water, and a radiation shield, it perhaps met the necessary conditions. Thus, the end of the dynamo marked much more than just internal cooling. It changed the fate of a world. It sealed the trajectory of a once wet and potentially habitable planet, turned arid and silent. At the start of this period, between 4.4 and 4.1 billion years, Mars was still a young planet. Its history was already marked by violent activity, and a colossal event was about to permanently transform its face. To understand this era, one must imagine a world in construction, struck by regular impacts that shaped its landscapes. These collisions had already left deep craters, faults in the crust, unstable terrains. The atmosphere was denser than today, rich in carbon dioxide and water vapor. On the surface, the first reliefs appeared, but without the future contrast's magnitude. In this scene, dominated by volcanoes and asteroids, an unprecedented impact loomed. Scientists call it the Borealis impact, a celestial body nearly 1,000 kilometers or 621 miles in size collided with Mars. The energy released was gigantic. A single impact reshaped the entire northern hemisphere, digging an immense basin and creating a profound asymmetry between the two halves of the planet. This event marked the origin of what would be called the Great Martian Dichotomy. The affected northern area became a vast depression, a basin that could much later host an ocean. This low-altitude depression could retain water or ice, because Mars, at that time, still knew temperatures allowing the presence of liquid water. The atmospheric pressure remained sufficient to maintain temporary rivers, scattered lakes, and a less hostile climate than observed today. But this impact did not stop at the north. The south suffered a crustal thickening. The impact redistributed matter, causing a uniform uplift of the crust. Mars then found itself divided in two, a low and relatively smooth north, a high and cratered south. This division remains one of the planet's most striking geological features, two worlds coexisting on the same globe. Beyond the topographical transformation, the impact triggered a sudden rise in temperatures. The ground and deeper layers were heated by the shock's energy. This warming, combined with the crust's fracturing, allowed underground water to circulate deeper. We then speak of hydrothermal circulation. Heated fluids spread through the cracks, modifying minerals, sometimes forming new ones. Comparable processes can be observed today on Earth in certain volcanic areas. During this phase, water plays a central role. It interacts with the rock, incorporates itself, and leaves its signature. Minerals such as phyllosilicates, capable of storing water at a molecular level, form. A part of Martian water then ceases to circulate freely and is fixed inside the rocks themselves. This underground storage becomes crucial for the planet's hydrological future. This trapping mechanism is an indirect but major consequence of the impact. Without this shock, the distribution of water would likely have been very different. These chemically altered regions, once traversed by hot fluids, still provide clues today. They contain mineral veins, altered layers, and signatures that allow us to trace the ancient water flows. Topographically, the Borealis impact leaves a visible imprint, a deep basin in the north, progressively filled with volcanic materials, sediments, ice, and dust. Yet, the mark of the impact remains present. The crustal thickness in the south far exceeds that of the north, witnessing a major redistribution of matter. This difference, still measurable, is a reminder of the past violence. The most convincing evidence is found in the topographic maps provided by space missions. The planet is not spherical. Its northern hemisphere is depressed. This depression is not the result of slow erosion, but of a singular event. Numerical simulation of a large-scale impact shows that a projectile of a size comparable to a small moon, launched at high speed, is sufficient to produce this asymmetry between north and south. Chronologically, this impact is placed between 4.4 and 4.1 billion years ago. These dates are based on studies of the oldest Martian surfaces, covered with craters, and on geological modeling. Mars, although already solidified, was still in a phase where large cosmic impacts were frequent. The Borealis impact fits into this key moment. This shock not only modified the crust, it may also have initiated environments favorable to complex chemistry. On Earth, life could have originated under similar conditions. On Mars, some suggest that hydrothermal circulations could have offered niches conducive to the appearance of organic molecules. Even in the absence of formal evidence, this hypothesis continues to inspire current research. The impact also ejected immense quantities of material all around the planet. These fallout materials, heated to white heat, contributed to locally raising temperatures, favoring other hotspots of hydrothermal circulation. This cloud of debris covered entire regions, provoking chemical reactions, altering surfaces, and modifying thermal dynamics over vast distances. The impact could also have introduced new elements to the Martian surface. If the impactor came from the outer regions of the solar system, it could have carried water or organic compounds. The analysis of the ejecta and their chemical composition remains at the heart of many hypotheses about exogenous contributions to Mars. The debate remains open, but the idea of an external chemical enrichment continues to fascinate. After the shock, the planet slowly cooled. The hydrothermal systems continued to operate for a period, long enough to alter the rocks and form minerals capable of trapping water permanently. This transformation left visible signatures in the composition of certain deep layers, still perceptible today. This cataclysm highlights the fragility of young planets. Mars, smaller than Earth, did not have the time or mass to stabilize its structure. This great dichotomy, unique in the solar system, illustrates this singular destiny. On Earth, such impacts also occurred, but they were integrated into a process of global equilibrium. Mars, however, retains the clear trace of this upheaval. Let us envision the Borealis impact as a live scene. A shockwave, flows of rock, a cloud of dust rising into the Martian sky. Beneath the surface, fluids infiltrate, alter the rock, create deposits. The sky clears. The planet is changed forever. The immediate effects diminish, but the topography remains transformed for eternity. The thickened crust in the south is not just a relief. It affects thermal dissipation, fracturing, future volcanic dynamics. The Tharsis Dome and its giant volcanoes will be born in this asymmetrical context. The planet's deep architecture, shaped by this shock, still influences the location of its great geological edifices today. This impact has thus influenced the distribution of water. The lower north could have hosted an ocean if conditions allowed. The thicker south may have stored water deep in the rocks. Some evaporated, some escaped, but a significant fraction became trapped for very long durations. Current data confirm this story. Topographical surveys show the depression in the north. Spectrometers detect hydrated minerals, Fan-like structures suggest ancient deltas. Everything indicates that the Borealis impact transformed Mars, physically and hydrologically. Today, Mars is dry, cold, swept by storms. But at the dawn of its history, it experienced an active and changing phase. The Borealis impact is a turning point. Without it, the planet would have had a different structure, a different water cycle, perhaps a gentler geological evolution. Scientists now consider this event a key to understanding. It influences volcanodynamics, erosion, and the distribution of caps. It shapes the planet's mineral memory. It inscribes into the rock an ancient story we are still trying to decipher. We are transported to the Noachian epoch of Mars, an era that extends between 4.1 and 3.7 billion years. Imagine flying over a still vibrant red planet, wrapped in an atmosphere much thicker than today's, dotted with expanses of water. At this time, carbon dioxide pressure varied between 0.5 and 1 bar, or approximately 7 to 14.5 psi, well beyond current values. Thanks to this dense envelope and the resulting greenhouse effect, the temperature sometimes exceeded the freezing point, allowing the formation of shallow seas. Not vast oceans like on Earth, but large bodies of stable water that may have lasted for tens of thousands of years. To a fictional observer, Mars would then offer the image of a bluer world, dotted with wet plains. The role of carbon dioxide is central to climate regulation. During this period, it efficiently trapped solar heat. Atmospheric humidity from evaporation briefly amplified this effect. Simulations show that the average temperature could then break the 0 degrees mark or 32 degrees, favoring the stability of surface waters. However, Mars' distance from the Sun made this warming fragile, alternating with cold phases where water froze or sublimed. Despite this instability, geological evidence suggests an ocean covered the low plains of the northern hemisphere. Sometimes called the Borealis Ocean, it would have represented up to a third of the water present at the time. Spread across the planet, this water would have formed a liquid layer several tens or hundreds of meters, or approximately hundreds to thousands of feet thick. This ocean, nestled in the north, would have filled depressions, while the higher south remained dry, shaped by ancient impacts. Proof of its existence comes from formations evoking shorelines, sediments deposited in the northern plains, and river networks that cross the heights to flow downward. Some craters show fan-shaped deltas, characteristic of river mouths. Jezero and Eberswalde are the most striking examples. Such deposits only appear after long-distance transport and a slowdown of waters as they arrive in a larger expanse. These deltas are surrounded by clay-rich areas, evidence of a tempered chemical environment. Phyllosilicates, composed of iron, magnesium, silicon, and water, result from the alteration of volcanic rocks by liquid water. Basalt, omnipresent on Mars, reacts under the influence of water by releasing ions that then form these hydrated minerals. Smectites, in particular, can swell, store water, and capture chemical elements. Their formation indicates a relatively neutral pH, conducive to complex chemical reactions, unlike other more acidic eras. To visualize their origin, one must imagine water trickling through rocks, dissolving some components and depositing others. This process transforms basalt into clay, and sometimes into carbonates if carbon dioxide interacts with the released ions. These carbonates, comparable to terrestrial limestones, are additional indicators of a humid climate and an active atmosphere. They show that water and carbon dioxide were trapped in the crust. reducing their presence in the air. This infiltration mechanism allows water to be stored in depth. It seeps through cracks, circulates in the rock, and forms hydrated minerals. On Mars, the natural porosity of volcanic rocks, reinforced by impacts and fractures, offers a conducive network for this retention. Thus, a significant portion of Martian water ended up trapped in the crust, isolated from the surface. In comparing Mars to Earth, the difference is striking. On our planet, water remains on the surface or at the poles. On Mars, the thinning of the atmosphere and the disappearance of the magnetic field led to the loss of liquid water. The question remains, where did it go? Some of it escaped into space, while another part got buried in the rock or froze underground. The Noachian era, rich in signs of a wet past, sheds light on this mystery. A large portion of the water seems to have hidden away since this distant era. During this era, the water cycle was fueled by precipitation or snowfall. Carbon dioxide thickened the atmosphere, trapping heat, even though the solar energy received was less than Earth's. Watercourses, even ephemeral, shaped the landscape, carving valleys, depositing sediments. The deltas of Jezero and Eberswalde demonstrate the duration of these flows, long enough to create stratified deposits, evidence of an active hydrology. Mineralogical data collected by rovers and orbiters confirm the presence of iron-magnesium clays in numerous Noachian zones. Their sheet structure and capacity to trap water indicate a formation in a wet environment. On Earth, such minerals appear in sedimentary basins or in altered volcanic environments. Their mere presence on Mars attests to the prolonged action of water on the rock. Carbonates, on the other hand, show that carbon dioxide was also captured in solid rocks, reducing its contribution to the greenhouse effect. Deep infiltration has also altered the chemistry of the subsurface. Water circulated through fractures, forming secondary minerals, altering the crust structure, stabilizing water at great depth. This water, isolated, does not easily come back up, except in cases of uplift or local warming. Even today, a significant portion of Martian water is trapped, invisible, but very much present. In the Noachian era, the solar system was still young. Bombardments were frequent. These impacts locally heated the crust, promoted water accumulation. Mars then entered a maturation phase where water became a geological actor. It eroded, transported, transformed. Traces of this era are visible today in mineral formations, valleys, and deposits. Imagine this ancient landscape: partially submerged plains, emerging hills, meandering rivers, volcanoes briefly releasing gases, rains followed by runoff. Mars, although cold, was animated by a water cycle capable of shaping its surface. To date this era, scientists use crater density and terrain analysis. The more cratered a surface, the older it is. Noachian regions, rich in craters, testify to a very ancient past. Many show signs of erosion or filling, signs of water action. These observations, combined with mineralogical surveys, confirm the presence of hydrated clays and a wet environment between 4.1 and 3.7 billion years ago. Another major point of this era lies in the storage of water. When we talk about several tens of percent, it means a large portion of the water was no longer on the surface, but locked in the rock. On Earth, rocks like shales and clays play the same role. On Mars, this process also captured carbon dioxide and carbonates, reducing the greenhouse effect, which may have accelerated global cooling and the end of liquid water periods. In parallel, water infiltrated more than a kilometer or 0.6 miles beneath the surface, forming clays like smectites and trapping water in the rock. This underground storage concerns a significant portion of Martian water, which never left the planet but hid in its crust. Today, in comparing Mars to Earth, the gap is apparent. Where Earth maintains its oceans, Mars lost its surface waters, but still retains their traces. This contrast is explained by differences in atmosphere, magnetism, and climate. Mars has frozen, but its past remains etched in its rocks. The lesson is simple. Water is never guaranteed forever. Without protection, a planet can lose what makes it habitable. In this Noachian period, Mars experienced a favorable time for water stability, mineral formation, and a milder climate dynamic. Space missions, with their instruments, gradually reveal the clues of this past. Jezero and Eberswalde have become the guardians of this memory, preserving the sedimentary layers of a time when water was still actively shaping the landscape. We are at 3.9 billion years ago. Mars already has a denser atmosphere than today and still retains expanses of liquid water in the form of seas or intermittent lakes. But its environment remains unstable, exposed to cosmic upheavals. It is in this context that the late heavy bombardment occurs, a series of massive impacts that strike several planets and moons. Mars bears two major collisions. One creates the Hellas Basin, the other the Argyre Basin. Beyond their magnitude, these events destabilize the crust, eject materials into the atmosphere, and trigger water losses that will permanently transform the red planet. Imagine Mars just before these shocks. The ground already shows signs of ancient water. The thicker atmosphere plays a partial protective role. Temperatures still allow at times the presence of water in certain areas, particularly in less exposed depressions. We can envision wet plains crossed by streams fed by precipitation. However, this climate is about to tip. The bombardment is imminent, and it will irreversibly upset the balances. The impact that shapes the Hellas Basin is of exceptional intensity. The resulting crater, nearly 2,000 kilometers or 1,243 miles wide, remains one of the largest in the solar system. A gigantic asteroid strikes the surface at very high speed, releasing energy capable of melting and vaporizing rocks. The heat also releases gases trapped in the crust, notably water vapor and sulfur dioxide. The latter, expelled in mass, almost immediately modifies the composition of the atmosphere. A second shock of slightly lesser magnitude creates the Argyre Basin further south. Here too, the effects are multiple: destruction of surface environments, violent tremors, potential tsunamis, and release of hot gases and water into the air. Incandescent debris falls for hundreds of kilometers. The atmosphere thickens, loaded with sulfur dioxide, and climatic conditions deteriorate across the planet. The released sulfur dioxide reacts with altitude moisture. These chemical reactions produce acid rains with very low pH. These precipitations dissolve minerals, alter rocks, and reinforce erosion. Simultaneously, the thermal energy from the impacts locally raises temperatures above freezing, even if only for a few days or weeks. Mars thus finds itself exposed to acidic storms in a fractured and searing landscape. The water vapor released fuels a temporary greenhouse effect. Sulfur dioxide partially traps heat, but this elevation doesn't last. The atmosphere lacks the mass and stability necessary to maintain these conditions for long. Gases escape, chemical reactions occur, and the planet cools down again. These periods of warmth are therefore brief, unstable, incapable of anchoring water on the surface for good. Another effect of the bombardment is the dissociation of water by light and gas escape. Ultraviolet rays break water vapor molecules, separating hydrogen and oxygen. The lighter hydrogen escapes into space. On Mars, with its weak gravity, this loss is facilitated. Each fragment of water thus broken represents a fraction of the global reserve that will not return. The process is amplified by the solar wind. Energetic particles hit the atmosphere, expelling atoms into space. Without an effective magnetic field, Mars cannot defend itself. This erosion, accentuated with each solar activity surge, gradually thins the gaseous envelope. Along with it, disappears the ability to maintain liquid water. Models show that during this time, the hydrogen escape rates could be up to 100 times higher than today. The Hellas and Argyre impacts thus catalyzed a leap in water loss. The vapor released by the heat is dissociated, then dispersed. These combined mechanisms contribute to the irreversible drying out of the Martian surface. The effects of this phase are paradoxical. Heat and acidity release even more water, but it joins an atmosphere that can no longer hold it. The more water evaporates, the more it is exposed to sunlight and wind. Some researchers believe that with a stronger magnetic field, this story might have been different. In a few millennia, the climate shifts towards cold, pressure drops, and Mars loses a significant portion of its ability to retain water. The scientific data come from multiple sources. The Hellas crater, immense and deep, shows signs of chemical alterations. Sediments indicate circulations of water and acidic fluids. Argyre, smaller, shows similar signs. Around it, fossil valleys and flow traces indicate temporary, but intense, runoff, perhaps in the form of warm lakes. Meanwhile, orbiters have measured hydrogen isotopes in the current atmosphere. The high ratio of heavy hydrogen suggests that light hydrogen evaporated over time. These data support models showing that photodissociation and solar wind have stripped Mars of a large part of its water. For a potential biosphere, the consequences are severe. Degassing, acid rains, and rapid cooling make the environment hostile. Even if a few temporary niches may persist, the stability necessary for the emergence of life is heavily compromised. Chemistry spirals, volatile elements escape, and any biological continuity becomes uncertain. Visualize the scene. Clouds of dust obscure the sky, sulfur vapors rise, toxic rains fall on a fractured crust. Water evaporates, then dissociates. In the impact basins, temporary lakes may appear, saturated with salts and minerals. Meanwhile, the upper atmosphere frays and hydrogen escapes day after day. This bombardment initiates a transition. It causes temporary warming, but accelerates the atmospheric loss. Without these collisions, Mars might have retained its water longer. But the process is initiated. To these impacts will be added the extinction of the dynamo and the slowdown of volcanism. Together, they close the water cycle. Today, the scars are visible. Hellas, Argyre, their reliefs, their sediments. Topographic measurements and mineral surveys confirm this violent past. The Martian exosphere continues to lose particles, but at a much slower rate. The remnants of this era help us understand how a planet can turn from a wet world to a frozen desert. This pivotal moment, 3.9 billion years ago, marks a turning point. Water begins to evaporate massively, reservoirs empty, conditions change. These losses are not anecdotal. They explain Mars's unique trajectory. Bombardment, lack of protection, and atmospheric gas volatility deeply transform the planet. Between 3.7 and 3 billion years, Mars undergoes a phase of profound upheavals. It's the time of the rise of Tharsis, a major event that will reshape the Martian surface and transform how water exists on the planet. In this crucial chapter, the gradual rise of this immense volcanic region will disrupt the topography, influence atmospheric pressure, and make the presence of liquid water on the surface increasingly unstable. Just before this transformation, the Martian crust is already formed but remains mobile. Mars is still traversed by intense volcanic activity. In the Western Hemisphere, a titanic accumulation of materials occurs, giving birth to the Tharsis Rise. This uplift spans thousands of kilometers or miles and houses several volcanic giants, such as Olympus Mons, Ascraeus Mons, Pavonis Mons, and Arsia Mons. All are part of the same geological entity, whose formation begins precisely at this time. The rise of Tharsis is not limited to eruptions. It's an entire remolding of the crust. Magma, heated in the depths, rises to the surface, accumulates, exerts pressure, and, upon emerging, forms thick flows. Sometimes, the void left by an empty chamber creates a collapse. The surrounding terrain rises, fractures, deforms. Over time, gigantic reliefs rise. This movement leads to a redistribution of internal tensions. New fault networks appear, not only in the Tharsis region, but also far beyond. Among the most spectacular consequences, we see the formation of vast flood channels. These valleys, like Kasei Vallis or Maja Vallis, bear the marks of exceptionally large water flows. Under the frozen layers, immense underground lakes would have been maintained in a liquid state thanks to the heat of the subsurface or to pressure. When the crust cracks, these reserves are suddenly released. A simple collapse can then release millions or even billions of cubic meters or cubic yards of water. These torrents carve valleys, carrying sediments over hundreds of kilometers or miles. Even if these volumes represent a small fraction of a hypothetical global ocean, the effect on a local scale is immense. The landscape is transformed by these destructive waves. To understand the presence of water under the ice in such an environment, one must imagine a cold planet, but whose interior remains warm. The pressure exerted by the upper layers and the internal heat allow water to persist deep down. This is a phenomenon observed on Earth in polar regions. Mars, at this time, presents analogous conditions. Meanwhile, eruptions release enormous quantities of gases. Water vapor and carbon dioxide escape with the magma. These gases, capable of retaining heat, can temporarily thicken the atmosphere. At the beginning of Tharsis's formation, they help maintain higher temperatures, favorable to liquid water stability. But this warming does not last. Studies show that over time, atmospheric pressure decreases. It falls below the critical threshold of 100 millibars, too low to allow water to remain liquid. Mars, despite its volcanic emissions, gradually loses its gaseous envelope. The solar wind and low gravity accelerate this erosion. In theory, massive degassing could have maintained a stable atmosphere, but Mars loses its gases faster than it produces them. Its magnetic field weakens, impacts accumulate, and the absence of active tectonics prevents any recycling. The atmosphere thins, making water increasingly unstable. With this drop in pressure, surface water begins to boil or freeze almost instantly. Even if the temperature occasionally exceeds zero, the liquid does not hold. Like on Earth in high mountains, the boiling point decreases with pressure. On Mars, it becomes so low that exposed water instantly transforms into vapor or ice. In this context, water withdraws into the ground or toward the poles. On the surface, it becomes rare. Only sporadic upwellings caused by eruptions or fractures give rise to fleeting floods. These floods fill basins, but the water eventually freezes or evaporates. The Hesperian transition marks this shift. It introduces a new dynamic: extensive volcanic plains, massive deposits, but a constant loss of pressure. In Tharsis, lava flows accumulate, a sign that volcanism remains active, but its emissions are no longer enough to reverse the trend. Large channels like Casevalis tell this story. Their dimensions reveal the power of the discharges. We imagine buried water pockets released by a collapse or a surge of heat. In just a few days, an ephemeral sea can appear, then vanish. These episodes create marked landscapes, but their duration is brief. Models suggest that liquid water persists only for a few days. Sometimes a thin layer of ice or a dusty cover delays its evaporation. But the general trend is clear. Mars becomes drier, colder. Water becomes unstable. It transitions from ice to vapor without remaining liquid. Only very specific conditions still allow ice to persist. A dust mantle can slow sublimation, but not stop it. Volcanism continues. Eruptions occur, but the atmosphere crumbles. Degassing no longer compensates for the losses. Without a protective magnetic field, the planet gradually loses its gases. The solar wind accelerates this escape, and the atmosphere depletes. On Earth, the magnetic field, tectonic plates, and volcanic activity maintain the atmosphere. On Mars, nothing like that. Tharsis, despite its power, cannot stop the collapse. The air becomes too thin, the water unstable. At the end of this period, Mars takes on its current face. The seas disappear, streams dry up, water retreats underground or at the poles. It freezes, it stagnates. On the surface, it vanishes. This world has never been static. It was a theater of fire and ice, of powerful movements and sudden torrents. When the Hesperian ends, volcanism decreases. Tharsis remains, but its influence wanes. The water, once visible, becomes invisible. The traces remain. The giant volcanoes are there, witnesses of this era. The valleys, carved by torrents, recount the last moments of an active cycle. Today's rovers traverse these terrains, searching for clues left by this forgotten history. To understand this era, scientists cross-reference data. They measure the terrain, analyze rocks, scrutinize channels. Each fragment collected feeds climate models, revealing the evolution of the atmosphere and geology. The isotopes of water and carbon dioxide betray the loss to space. The ratio of light to heavy hydrogen increases, proving that water evaporates without return. Even if Mars once expelled vast volumes of water, it couldn't retain it. In a few 100 million years, Mars transitions from a world where water flows to an almost dry planet. Channels, lakes, floods are but memories. The landscape is frozen, the water buried. This shift is the result of three dynamics: the uplift of Tharsis, which restructures the planet, the sharp drop in pressure, making water unstable, and the global cooling, which freezes the surface. This moment, between 3.7 and 3 billion years ago, is a turning point. The surface transforms, the water fades, the climate collapses. Volcanism wasn't enough. The atmosphere emptied, the water fell silent. Between 3 and 1 billion years before our time, Mars enters a phase called the early Amazonian. This period follows wetter times, when liquid water still existed on the surface. The climate changes, the atmosphere dwindles, and the water cycle transforms. Two major phenomena mark this era: residual volcanic activity in the Elysium region and the migration of underground ice, giving rise to a porous cryosphere and brines enriched with salts, capable of remaining liquid at very low temperatures. The planet's cooling is already well underway since the end of the Hesperian. Large extents of liquid water have disappeared. The atmospheric pressure is too low to keep water stable on the surface. Yet some volcanic eruptions occur, especially in the Elysium region. Even weakened, this volcanism still releases vapor and various gases, potentially generating some local moisture or fine temporary sheets around active areas. Elysium, northeast of Tharsis, remains an identifiable volcanic region, although less imposing. It still features elevations like Elysium Mons and Hecate's Tholis. The activity is discrete but real. This residual volcanism releases carbon dioxide and vapor from the depths. Even though this activity can't rival past eruptions of Tharsis, it is enough to briefly sustain small-scale thermal and chemical effects. When the lava breaks through the crust, it releases volatile gases that rapidly escape. A discharge of vapor is observed, sometimes accompanied by sulfur or carbon monoxide. On Earth, such outgassing fuels rains in seas. On Mars, they are lost in an atmosphere too thin to trap moisture effectively. Precipitations remain rare, fogs ephemeral. Water forms neither seas nor enduring lakes. These emissions, though fleeting, briefly alter the immediate surroundings. Sheets of vapor float above the flows. Some puddles or streams may appear, but they dissipate quickly. The atmosphere, too thin, supports no sustained hydrological cycle. Low gravity, global cooling, and the lack of magnetic protection favor the escape of gases into space. Meanwhile, the ice buried beneath the surface begins to migrate. Water moves to deeper layers, less exposed to extreme cold. The surface dries out. The Martian cryosphere sets in. It forms a layer where ice is trapped in soil pores, kilometers, miles deep, particularly at mid and high latitudes. It becomes the planet's main water reservoir. In this porous cryosphere, ice occupies the smallest interstices. Isolated from the atmosphere, it escapes evaporation and chemical dissociation. It's a sanctuary of frozen water, protected from the aggressions of the spatial vacuum. Even if the surface becomes arid, these deep ice layers persist for very long periods. There, at the heart of the cryosphere, chemical interactions can occur. Some soil salts, like perchlorates, react with the ice. These compounds modify the behavior of water, lowering its freezing temperature. On Mars, their presence favors the formation of liquid brines at extremely low temperatures. These rare and salty liquids become essential elements for understanding the planet's hydric evolution. These brines, stable at -60 degrees, 76 degrees, only form under specific conditions. The mixture of water and perchlorates delays freezing. Even in intense cold, the water retains some fluidity. These are very concentrated solutions, similar to the salty waters found in some frozen deserts on Earth, but at much more extreme temperatures. Protected from the vacuum by rock, buried under layers of soil, these brines can persist. A small source of volcanic heat or geothermal heat is enough to maintain these liquid pockets. Thus, they resist hostile conditions and prolong the presence of water in liquid phase in the Martian depths. These environments are of great interest for the search for life. On Earth, bacteria survive in hypersaline environments. On Mars, although there is no proof of an active biosphere, these pockets could represent refuges where life could have persisted. Perchlorates, rich in chemical energy, could provide resources to potential microorganisms. However, the amount of water involved remains minimal. These are not seas, nor even lakes, but small traces of moisture. Their presence depends on the relief, internal heat, chemical composition, and ice distribution. As Mars cools and its atmosphere escapes, these refuges become increasingly rare. By the end of this era, around 1 billion years, the cryosphere extends over almost the entire planet. In some regions, ice forms nearly permanent layers. Water, increasingly immobile, slowly circulates through the fractures. Volcanism, nearly extinct, no longer provides the energy necessary for intense hydric activity. Mars becomes dry, cold, and frozen. To study this period, scientists rely on clues left in the rocks. Orbiters and rovers have identified minerals indicative of ancient water movements. Altered layers, traces of saline fluids, reveal that brines have existed. The Elysium region remains one of the few places where this late activity is still visible. Computer models attempt to quantify the heat still available at this time. An active volcano, even modest, can cause local ice melting. Water then flows, meets the soil salts, and forms these brines. Elysium and its surroundings may have retained, a little longer than other regions, favorable conditions. These saline pockets represent one of the last bastions of liquid water on Mars. They offer a key to understanding the limits of habitability. A rover could, by digging a few meters or yards, reveal these traces. Once heated, these brines would reveal their composition and, perhaps, organic clues. The formation process of these brines relies on a delicate balance. Perchlorates absorb moisture and lower the freezing temperature. At minus 60 degrees, 76 degree, the water does not entirely freeze. These solutions, although extremely cold, remain liquid. In the absence of direct contact with the atmosphere, they resist sublimation. The Martian soil also contains other salts. Sulfates, chlorides, all contribute to this complex chemistry, but perchlorates are the most effective in keeping the water liquid. That's why they are at the center of research. Volcanism provides heat and materials, and the brines become the last traces of water. Ancient Amazonian is a desert of dust and rocks, where only detailed analyses can detect signs of hydric activity. The heat dissipates, the magnetic field fades, the atmosphere disappears. The cryosphere remains the last bulwark against this total loss. As we approach the recent Amazonian period, the water cycle contracts further. Ice buries itself ever deeper. Radar today still shows the existence of large ice pockets. As for the brines, they persist in rare niches where pressure, temperature, and composition allow. Thus, between 3 and 1 billion years ago, Mars experienced a crucial stage. The volcanism of Elysium releases its last vapors, while ice descends into the crust. The first perchlorate brines appear, the last forms of liquid water in a declining world. Mars slowly fades, but retains a little of its aqueous memory in its depths. The surface remains inhospitable, cold and dryness prevail. Yet, in some cavities, a bit of water persists. The early Amazonian does not mark the end, but a transformation. Water does not disappear. It changes state, location, and role. It becomes underground, discrete, but never absent. For a billion years, Mars has entered a phase that scientists call the recent Amazonian period. This epoch is characterized by large variations in the tilt of the rotation axis, known as obliquity. Unlike Earth, whose angle varies little, that of Mars can oscillate between 15 and 45 degrees. These shifts affect how sunlight reaches different regions of the planet, profoundly altering the circulation of water. The poles then undergo cycles of glaciation and deglaciation, alternating between accumulation and loss of ice. To grasp the effect of these variations, imagine the North Pole tilting toward the sun during peaks of obliquity, then turning away during low phases. This causes major thermal reorganization, sometimes favoring the partial melting of caps, other times promoting their growth. Water then migrates between the poles, mid-latitudes, and the subsurface. When the poles receive more heat, part of their ice sublimates, enriching the atmosphere with vapor, which redeposits elsewhere. Conversely, during cold phases, the water refreezes at the poles. These movements produce stratified deposits, visible as layers of ice mixed with bands of dust. They are mainly observed in the north and south caps, where the temperature remains low enough to preserve these climate archives. The dynamics of these deposits shed light on how water travels on Mars, obeying the pulsations of obliquity. Scientists hope, by studying them, to reconstruct the recent hydrological history of the planet. Outside the polar regions, glaciers have been identified in intermediate latitude zones. Hidden under layers of sediment or dust, these glaciers often nest in valleys or along slopes oriented north or south. They formed at a time when high obliquity favored the migration of water vapor to these regions, which slowly accumulated ice before losing it during the return to colder cycles. These glaciers are recognized through images taken by orbital probes, which reveal lobe-shaped forms at the base of topographies or curved structures in depressions. The radar penetrates the surface and detects ice hidden under several meters or feet of soil. These buried reserves show that water still persists in the Martian crust. The challenge is to understand the conditions that cause it to melt or disappear. Researchers have also focused on ice scarps, cliffs where erosion or recent impacts have exposed almost intact layers of ice. In some places, it is found less than 1 meter, or 3 feet, deep. These structures offer direct access to preserved water, and their study might provide valuable insights into the evolution of obliquity over time. In parallel, instruments in orbit have detected signals in certain regions suggesting the presence of liquid water or highly saline brines. It is in the Valles Marineris canyons that these indications are most marked. There, the radar reveals areas that might contain pockets of hypersaline liquid, capable of remaining fluid despite freezing temperatures. These brines awaken great scientific interest, as they might represent the last forms of stable liquid water on Mars. Concentrated brines and salts are a major topic for astrobiologists. They recall certain very salty lakes on Earth, where microorganisms manage to survive. On Mars, they could be hiding beneath the surface, sheltered from the cold and radiation. The salts they contain lower the freezing point, allowing a form of partial water, compatible with extreme aquatic niches. Even though the current environment is very hostile, the idea of microscopic life subsisting there remains conceivable. To validate the existence of these brines, more detailed radar measurements will be necessary. Models predict that they form at the pace of obliquity changes. When the atmosphere warms up, more vapor escapes from the poles and can condense in the canyons. There, the depth protects from large temperature fluctuations, allowing the brines to persist longer than in other regions. The origin of the dissolved salts would be linked to the alteration of rocks. Under a milder climate, liquid water could have extracted these minerals, which accumulated in deep areas. Over time, the drop in temperature and pressure transformed them into frozen or semi-liquid layers. Obliquity oscillations then maintain a cycle between partial melting and refreezing, shaping a complex underground landscape. Geothermal activity could also play a role. Although weaker than on Earth, Mars's internal heat might be enough to prevent some brine deposits from completely freezing. In the most favorable zones, this heat could form stable, well-insulated pockets. Some radar anomalies recorded in the canyons suggest this, indicating the persistence of liquid pockets, linked to the planet's slow heat loss. The recent Amazonian period began 1 billion years ago. Since then, Mars has seen its atmosphere thin out, its pressure drop, and its climate cool. Yet, the obliquity has marked brief episodes of water redeployment, causing partial melting of the caps and burial of ice in the mid-regions. These cycles have left glaciers, witness to this long and changing history. Simulations are now attempting to quantify these oscillations. They take into account atmospheric density, available vapor, the planet's rotation speed, and the evolution of its axis. The data transmitted by probes, rovers, and landers allow testing these hypotheses. The strata observed in polar or glacial deposits could correspond to an accurate record of these changes. Despite its harsh climate, Mars remains surprisingly active. Far from being frozen, it shows signs of water circulation, ice concentration, and persistence of liquid states. Its axis oscillations shape this cycle, redistributing light, temperature, and humidity. This discrete, slow, but constant dance continues to transform the face of the red planet. Over time, Mars has seen its atmosphere slowly thin, losing precious parts of its gases and water. This phenomenon, called atmospheric escape, is central to understanding the planet's history. It reveals how Mars could once have been wetter and why it became so dry. To track these traces, scientists rely on detailed observations and continuous measurements aimed at reconstructing the extent of this loss into space. Atmospheric escape corresponds to the release of gas particles that, after crossing the planet's gravitational limit, vanish into space. On Mars, this process is amplified by the action of the solar wind. Charged particles, launched at high speed from the sun, strike the upper layers of the Martian atmosphere. Upon this impact, oxygen or carbon atoms can be propelled far from the planet, carried away into the void. study these mechanisms, a space mission was launched, MAVEN. Since 2014, this probe has been monitoring the movements of Martian atmospheric particles. Thanks to sophisticated detection instruments, it measures the ions escaping, their speed, and their frequency. The data it collects helps track in real time the losses affecting the high atmosphere of the red planet. The results are impressive. MAVEN measured a massive flow of oxygen and carbon ions, ejected at a rate of 10,000 billion particles per second. This quantity suggests that Mars is still losing a significant fraction of its atmosphere today. This phenomenon, accumulated over billions of years, could represent the equivalent of a half of an Earth's ocean disappeared. A half of an Earth's ocean corresponds to a volume of water that, evenly distributed on the surface, would cover the planet with a significant layer. While this estimate is theoretical, it nonetheless reflects the cumulative loss of water through interaction with the atmosphere. This gradual disappearance has contributed to drying the surface and limiting Mars's ability to sustain an active water cycle. The main cause of this vulnerability is the absence of a global magnetic field. Unlike Earth, which is protected by its magnetosphere, Mars only has residual traces of magnetism. As a result, the solar wind more easily reaches the upper atmosphere and promotes the dispersion of light gases into space. The losses are not constant. They vary according to solar activity. During periods of high intensity, the particles ejected by the sun are more numerous, and atmospheric escape accelerates. MAVEN monitors these fluctuations to evaluate the most critical periods. One element is particularly sensitive to these conditions: hydrogen. Derived from water, this light atom easily reaches the upper atmosphere. It is particularly affected during large dust storms, when atmospheric circulation changes and the upper layers warm up. During these moments, the rise of hydrogen accelerates. Martian dust storms, capable of covering the entire planet, strongly modify atmospheric dynamics. By warming the upper layers, they allow hydrogen to more easily overcome gravitational limits. Recent observations show that these events lead to marked increases in escape rates. MAVEN's instruments record these variations with precision. By comparing calm periods to turbulent ones, researchers observe how irregular the loss of hydrogen is. This process, far from being linear, depends heavily on local and solar conditions. During certain situations, especially during solar eruptions or at specific points in the orbit, the escape can become spectacular. Bursts of particles strike the upper atmosphere, ripping ions away at high speed. Hydrogen, in particular, easily crosses the gravitational barrier, contributing to the gradual thinning of the Martian air. These observations strengthen the idea that, in the past, Mars must have had a denser atmosphere capable of sustaining surface water. The lack of an effective magnetic shield gradually exposed the atmosphere to repeated solar wind assaults. This slow erosion significantly altered the planet's environment. Today, some of Mars's water remains, but it is embedded in ice, trapped in polar caps or bound to minerals. The atmosphere, however, contains only a tiny fraction of it. The loss of half of an Earth's ocean is a striking image, illustrating the major climatic upheaval Mars has experienced. For scientists, these results also shed light on the future of human exploration. Any attempt to settle on Mars will have to consider this fragile atmosphere and active escape process. The data provided by MAVEN is therefore invaluable for anticipating long-term constraints. Some hypotheses mention ambitious solutions, such as creating an artificial magnetic field between Mars and the Sun. If such a device came to be, it could reduce atmospheric losses and prolong the stability of the Martian environment. For now, these projects remain theoretical. Continuous monitoring of seasonal variations, especially during large dust storms, remains a priority. These events, though rare, allow the measurement of the most extreme responses of the Martian atmosphere. The collected data helps to understand the role of each parameter in gas escape. The figures from MAVEN's measurements make it possible to quantify the losses. By extrapolating density, velocity, and affected area, researchers estimate the total flux of lost ions. These values are then used to model atmospheric evolution over several billion years. Despite some uncertainties, the conclusions converge. A large portion of the water and air available on the surface has dissipated into space. This loss is related to the gradual erosion induced by solar activity. MAVEN's results are among the most convincing for documenting this transformation. The drop in pressure today makes it impossible for liquid water to remain stable on the surface for long. As soon as it appears, it evaporates or freezes almost immediately. This vicious circle prevents any natural recovery unless massive external interventions occur. Mars still retains some resources, but they are limited. Some pockets of ice or moisture persist, sometimes released during earthquakes or eruptions. Despite this, the balance remains very deficient. The planet continues to lose particles at a slow but steady rate. Understanding atmospheric escape in detail allows us to evaluate Mars's climatic past and consider the habitability of other planets. This phenomenon could apply elsewhere in the solar system, or even to exoplanets, where unprotected atmospheres might suffer a similar fate. The MAVEN mission continues to play a central role. Thanks to its observations, it refines our understanding of the mechanisms at play and helps predict future evolution. Every storm, every variation in solar activity is an opportunity to gather new data. Far from being static, the Martian atmosphere still reacts to disturbances. The dust raised, the flows of particles, the seasonal changes all contribute to this shifting picture. Even in its fragility, Mars remains an active planet, sensitive to the slightest solar variation. The study of Mars thus offers a valuable lesson. It reminds us that water, so commonplace in our eyes, can silently be lost if the necessary conditions for its retention are not met. Through MAVEN's data, scientists gradually reconstruct the fate of the red planet and draw inspiration to better understand other worlds in our universe. Under a dust-laden sky, above the silent expanses of Mars, attention turns to its invisible depths. Over the years, space missions have shown that Martian water neither completely evaporated into space nor froze on the surface. A significant portion remains trapped in minerals or buried as ice and brines. These invisible reservoirs play a key role in the current Martian water cycle. To understand the dynamics, one must explore the water-containing rocks, the buried frozen sources, and the ever-moving water cycle. This chapter delves into the aquatic secrets of Mars and reveals how researchers reconstruct the ancient distribution of water while detecting signs of an active cycle. The journey begins at the surface, within the rocks themselves. By observing eroded craters and plateaus, orbiters have identified hydrated minerals. These clays, or phyllosilicates, contain water integrated into their crystalline structure. Formed at low temperatures in the presence of liquid water, they retain this water long after the climate has dried up. A large part of Martian water now disappeared from the surface, thus remains buried in these rocks. According to estimates, up to half of the planet's ancient water could still be found in them, partially revealed through comparisons between past water volumes and the amounts still detectable. The explanation for this retention lies in the very formation of the minerals. In aqueous environments, some crystalline structures integrate water durably. Some hot underground circulations, called hydrothermal, have formed rocks rich in water, such as opalines, which are also hydrated silicas. These minerals are identified through spectral signatures detected by probes and rovers. A large quantity of Martian water has thus dispersed into the crust's rocks, out of immediate reach. But Mars also hides reserves in its depths. Researchers estimate that a significant fraction of the water is in the form of porous ice or brines, more than 1 kilometer or 0.6 miles below the surface. These brines, salty solutions, remain liquid at very low temperatures. Trapped in pressurized pockets under layers of rock and ice, they neither freeze completely nor evaporate. The pressure and the salt are enough to stabilize their state. To detect these pockets, researchers use radar's onboard orbiters. These instruments send waves into the ground and measure the reflected signals. When a contrast appears between two layers, the presence of water or ice is suspected. Some echoes suggest the presence of buried saline pockets. These results reinforce the idea of a dynamic underground world where water still circulates discreetly. Recent impacts have also provided clues. Sometimes, when a small meteoroid strikes the ground, clear patches appear, which darken over time. This is likely exposed ice, which rapidly evaporates in the dry atmosphere. This ice is located a few meters or feet below the surface, well beyond the polar caps. Mars, therefore, seems to have a much more extensive buried water reserve than previously expected. Instruments like SHARAD, a radar mounted on an orbiter, have confirmed these clues. Capable of penetrating up to several hundred meters or yards, it reveals internal layers with high permittivity, suggesting ice or brines. In several regions, very pure layers and others saturated with salt have been identified. This reveals a more active water cycle than previously thought. With these different types of storage, Mars constitutes a hidden reservoir of water. The minerals, buried ice, and brines indicate that water has not entirely left the planet. The solar wind and the thin atmosphere contributed to the losses, but a significant portion has remained trapped. This underground water is not just a geological fact, it also represents a potentially life-friendly environment. The idea of microbial life sheltered in these moist areas is gaining ground. On Earth, bacteria are found in very salty or buried environments. Mars, despite its harsher conditions, might harbor similar niches. Researchers hope to one day drill deep to analyze these pockets. Meanwhile, radars and spectrometers already give us valuable clues about these protected areas. The Martian water cycle is unlike Earth's, but it has not disappeared. The polar caps are only a visible element of this system. A large part of the water is trapped in the crust, whether in minerals or ice near the surface. Seasonal variations can cause water migrations, sublimation, or even underground reconcentrations. Even if this cycle has weakened over time, it still influences the terrain and certain geological processes. This cycle also has visible effects: landslides, gully formations, surface collapses. Changes in the planet's tilt redistribute sunlight, which slowly moves the ice. By observing the polar layers or certain regions of the crust, we perceive signs of recent migration. These structures are not static. They continue to evolve slowly. This awareness has led scientists to revise their calculations. It was once thought that Mars had almost completely lost its water. In reality, a large quantity of water is still present, but in invisible forms. Researchers combine gravimetry, spectroscopy, radar, and field analyses to quantify these stocks. When signals change noticeably, it often indicates a significant presence of ice. It is also necessary to differentiate hydrated minerals from ice reservoirs. The former contain water at the atomic level. The latter can change state depending on temperature or pressure. The salts present in some areas lower the freezing point. This allows water to remain liquid even in very cold conditions. Thus, Mars's water budget has been shaped over billions of years. Recent research shows that the planet still retains a significant portion of its water. Data suggests that up to half of the ancient water might still exist in minerals. Another, more discrete portion might be hidden in porous ice and deep brines. These pockets, sometimes pressurized, react slowly, but they are not inert. This reality restores potential habitability to Mars. If microbial life existed, it might have sought refuge in these damp underground nooks. The next missions, by drilling deeper, may one day deliver a sample. With it, perhaps the evidence that life managed to thrive, even briefly, below the Martian surface. Imagine that you can travel through the dust and rock of Mars to dive into its heart. For a long time, scientists thought they would find a well-defined metallic core, directly overlaid by the solid mantle. But the seismic waves recorded by the InSight mission told a different, much subtler story. They revealed the existence of an entirely molten silicate layer, a real liquid cap resting on a core smaller and denser than expected. This is not a minor detail. It changes the entire way we reconstruct the thermal history of Mars and how its magnetic field, that protective dynamo, could have disappeared. What exactly is a molten silicate layer? Silicates are minerals based on silicon and oxygen, very common in rocks. On Earth, they make up the bulk of the mantle. Here, on Mars, a deep portion of these rocks would have remained liquid, like a very hot soup trapped between the metallic core and the solid part above. This implies that the boundary between core and mantle is not where we imagined it. Seismic waves crossing this carpet of molten rock behave differently, and it's this difference that researchers detected. Why is it mind-blowing for Martian science? Because it was thought that Mars's internal energy had decreased early enough to almost freeze the entire interior. If a layer is still molten today, it means the planet has retained more deeply enough residual heat. It also helps explain why the Martian dynamo stopped. The way heat dissipates and how the core cools directly affects the movements of the liquid metal, generating this magnetic field. A smaller core, surrounded by a partially molten mantle, does not react like a larger homogeneous core. Now let's leave the depths to return to the surface, in a place you might already know, the Jezero crater, where the Perseverance rover is exploring an ancient delta. Very particular rocks have been spotted there. They are rich in silica and contain quartz, chalcedony, and opal. These names evoke semi-precious stones, but here it's their formation method that interests us. They can deposit when hot water, called hydrothermal, circulates through rock fractures, dissolves elements, and redeposits them as it cools. This means that at one time, the water on Mars was not just cold on the surface. It could also circulate deeply, hot, mineralized, conducive to complex chemical reactions. Let's simplify the idea. Imagine a terrestrial hot spring, like those in Iceland. Water travels through hot rocks, becomes laden with minerals, and then when it rises and cools, it can leave behind silica deposits. On Mars, Perseverance has found rocks resembling this type of deposit. Quartz or opal are forms of silica. Chalcedony is a microcrystalline quartz. Their presence combined can indicate an episode where the planet's internal heat allowed the fluid circulation. Why is this crucial for life? Because these hydrothermal environments are refuges on Earth, where microorganisms thrive thanks to heat and minerals. This doesn't prove that life existed on Mars, but it shows that favorable conditions, heat, water, minerals, might have been established. And silica-rich rocks can trap and preserve microscopic traces, like shapes or molecules, for billions of years. That's exactly what we dream of finding: fossil biosignatures. Science Direct ResearchGate. Perseverance, still at Jezero, carries a crucial instrument, the RIMFAX radar. Imagine a medical scanner applied to a planet. The radar sends waves into the ground and listens to their echo to reconstruct the buried layers. Thanks to this underground eye, researchers have detected stratifications typical of a lakebed, successions of sediment layers deposited by water that flowed and settled over time. In short, the Jezero crater was indeed occupied by a lake, and not just a small pond lasting a few days. Why does this reinforce the idea of a habitable past? Because still or slow-moving water, like that of a lake, allows sediment to accumulate slowly, in regular layers. This type of environment is ideal for preserving chemical or biological traces, much like terrestrial lake sediments sometimes keep leaves, pollens, remains of insects. On a Martian scale, we hope for fossilized organic molecules or mineral structures formed by microorganisms. RIMFAX offers a geological map in depth that guides the rover towards the most promising layers. Observations have shown that these sedimentary layers extend at least several dozen meters or hundreds of feet in depth, which suggests a long and repeated history, multiple cycles of deposition, water withdrawal, and return. The lake was not just a one-off event. This could mean that at one point, Mars experienced a climate that maintained stable water on the surface long enough, at least in certain basins. Now, let's turn to a small flying hero. Ingenuity, the tiny helicopter companion to Perseverance, was designed for 5 demonstration flights to prove that flight was possible in an atmosphere 100 times thinner than Earth's. The result, 72 flights, 3 years of adventure, miles or kilometers traveled close to the Martian ground. A true pioneer. But in January 2024, during the 72nd flight, one of its blades was damaged. The mission had to stop. Ingenuity remained standing, still able to communicate, but unable to take flight again. Why a helicopter on Mars? because orbiters see the surface from above, but lack detail. Rovers see very well, but only at ground level, and move slowly. Ingenuity filled the gap. A fast scout, capable of finding safer paths, going to a point of interest inaccessible to wheels, mapping terrains in a few minutes. With every flight, it proved how much aerial reconnaissance could help. On a planet where the air is 1,000 times thinner than ours, spinning a blade fast enough to generate lift is a feat. Ingenuity flew thanks to very light rotors that spun several thousand revolutions per minute and sophisticated navigation algorithms. It was largely this navigation system that betrayed it in the end. The ground was too uniform, too little contrasted, which disrupted its optical speed sensors. The final crash was not brutal, but sufficient to damage a blade and end the adventure. Mars's water hasn't completely disappeared. It hid. Orbital instruments, particularly the Shared radar and the study of recent craters, have revealed the existence of ice beneath the surface, sometimes just a few meters or yards deep, up to about 30 degrees latitude. In other words, not just at the poles, but also in regions more easily accessible for future explorers. For a manned mission, it's a treasure. Water for drinking, for making oxygen, for producing fuel. How do we know this ice is there? First, when a small meteoroid creates a crater, it sometimes exposes very bright material that darkens in a few days. That's ice, laid bare, sublimating quickly in the dry atmosphere. Then, orbital radars like Shared send waves into the ground. When these waves encounter an ice layer, they send back a specific signal. By mapping these signals, we detect pockets of ice at various depths. These reserves aren't homogeneous. Some areas contain very pure ice, others ice mixed with dust or salts. Sometimes, this ice is found less than a meter or yard deep, other times at several dozen meters or tens of yards. It seems to have been deposited by ancient, wetter climates or moved by the variations in Mars's tilt, which redistribute ice between the poles and mid-latitudes over cycles. Europe has not said its last word. The long-delayed ExoMars mission has found a second wind. The Rosalind Franklin rover, named after the pioneering British scientist of DNA structure, is now set for a launch planned in 2028, with an arrival on Mars around 2030. The United Kingdom is building a European landing platform, while NASA will provide the launcher and other elements. The goal, to drill down to 2 meters or 7 feet deep, much more than Perseverance, to seek rocks that have never been exposed to Mars's harsh atmosphere. Why 2 meters or 7 feet? Because the deeper we drill, the more likely we are to find well-preserved organic molecules. On the surface, radiation and oxidation quickly destroy or alter delicate traces. At 2 meters or 7 feet, the rocks have been sheltered for billions of years. Rosalind Franklin will analyze these samples in situ, thanks to a miniature laboratory integrated into the rover. The chosen site, Oxyoplanum, is rich in clays. These hydrated minerals, already mentioned in your initial script, are excellent for trapping water and organic molecules. This makes it a prime target for the search for biosignatures. The European approach aims to complement American missions. While Perseverance stores samples for a future return to Earth, Rosalind Franklin will analyze them on-site in depth. 2 strategies, 1 goal: to answer the question, did life ever exist on Mars? Finally, a burning question. How to bring back to Earth the precious tubes filled with Martian cores the Perseverance carefully collects. The Mars Sample Return Program, initially planned jointly by NASA and the European Space Agency, was supposed to return these samples by 2040. But costs have skyrocketed, deadlines have lengthened, and plans have had to be revised. Today, several more agile scenarios are being studied, reducing the size of the vehicles, involving more private partners, simplifying the architecture. Dates such as 2035 are being considered if a streamlined version is adopted. Why is it so complicated? To bring back Martian rocks, a vehicle must land on Mars, retrieve the tubes, place them in a small Martian rocket, take off from Mars, which is unprecedented, rendezvous in orbit with a vessel that receives them, and then safely return to Earth, avoiding any cross-contamination. Each of these steps is a first. Moreover, money and logistics are significant factors. Governments must be convinced that the investment is worthwhile, while other space, lunar, or terrestrial projects compete for budgets. The involvement of commercial companies such as SpaceX or Blue Origin is now being considered. Their heavy launchers could simplify some steps and reduce costs. NASA is also not ruling out other architectures, such as cleaning or pre-treating the samples directly on Mars to reduce the mass to be transported. Nothing is decided yet. The roadmap must be finalized in the coming years. For science, the return of samples is the holy grail. On Earth, we have incomparably more powerful laboratories than anything that can travel on a rover. With rocks from Mars in hand, we can measure isotopes, detect trace organic molecules, precisely date events, and confirm, or not, evidence of ancient life. These discoveries reveal a common thread: water. It was on the surface, in the form of lakes, rivers, deltas. It percolated deep, warm, mineralized. It froze into ice, escaped into space as hydrogen. It is still hidden in clays and underground glaciers. The question is no longer, was there water on Mars? But, where did it go? How did it circulate? And what did it leave behind?